Bismillahirrahmanirrahim. Dear students, I am Dr. Uh, M. Salim Akhtar, Associate Professor of Chemistry. Now we are discussing the reaction dynamics, chem4146. This is our lecture number 39 regarding reaction dynamics. Dear students, today we will discuss relaxation method for first order opposed by first order reaction. That is how we can study the first order opposed by first order reaction with the help of relaxation method. Dear students, consider the following reversible reaction at equilibrium initially, which is perturbed by some way and the reaction moves in backward direction to nullify the effect of perturbation. Now, dear students, consider the following reversible reaction at equilibrium initially, which is perturbed by some way and the reaction moves in a backward direction to nullify the effect of perturbation. Reaction is A reversibly react with B with forward rate constant Kf and backward rate constant Ab. When T is equal to T equilibrium, when T is equal to T equilibrium, concentration of A is A small a and that is equal to B, that is the concentration of uh, component B, product. When the concentration, when the time is equal to T, then the concentration of A becomes A plus X and concentration of B becomes B minus X. Since uh, when the reaction was perturbed, then reaction go back what direction, so the concentration of A will increase and concentration of B will decrease. Initially, when time was at equilibrium, concentration of A was A and that of B was B. When T is equal to T, concentration of A becomes E plus X and concentration of B becomes B minus X. Where small a and small b represent the equilibrium concentration of A and B at initial equilibrium, whereas A minus X and B minus X represent the available concentrations of A and B respectively at time t. Now, dear students, where a and small b represent the equilibrium concentrations of A and B at initial equilibrium, whereas A minus X and B minus X represent the available concentration of A and B respectively at time t. The concentration of B decreases with time to attain new equilibrium and becomes constant again at final equilibrium. That is, the concentration of B decreases with time to attain new equilibrium and becomes constant again at final equilibrium. X and X naught are deviation of the concentration of B from its final equilibrium concentration at time t and t equilibrium respective. Once again, where small a and b represent the equilibrium concentrations of A and B at initial equilibrium, whereas A minus X and B minus X represent the available concentration of A and B respectively at time t. The concentration of B decreases with time to attain new equilibrium and becomes constant again at the final equilibrium. Dear students, and becomes constant at final equilibrium. X and X naught are the deviations of concentration of B from its final equilibrium concentration at any time t and t equilibrium respective. That is, X is the concentration of B and X naught is also the concentration of B at time t and t naught equilibrium respective. Now, dear students, rate of forward reaction is given by, according to law of excitation, Rf, that is equal to Kf into A plus X. Kf into A plus X. This is equation number 1. Similarly, rate of backward reaction is Rb, that is equal to Kb into B minus X. This is equation number 2. That is, again, the rate of forward reaction is given by, according to the law of excitation, Rf is equal to Kf into A plus X. This is equation number 1. Rate of backward reaction is Rb, that is equal to Kb into B minus X. This is equation number 2. dx over dt, the net rate will be equal to dx over dt, that will be equal to rate of backward reaction minus rate of forward reaction, that is RB minus RF. Now dear students, putting the values of RB and RF from equation 1 and 2, we will get dx over dt, that is equal to kb into b minus x, that is the b minus x is the rate of backward reaction, minus kf into a plus x, this is the rate of reaction for the forward reaction. Dx over dt, now we multiply, open the brackets, kb into b minus kbx minus kf into a minus kf into x, that is we have opened the brackets and multiplied kb and kf respectively, then we get dx over dt, that is equal to kb minus kb into b minus kbx minus kfa minus kfx, this is equation number 3. Once again, the rate of forward reaction is given by Rf is equal to Kf into concentration of A, that is A plus X. This is equation number 1. Similarly, the rate of backward reaction is Rb, that is equal to Kb into concentration of B, that is B minus X. Now the rate of reaction is equal to rate of backward reaction minus rate of forward reaction. Putting the value of Rb and Rf from equation 1 and 2 respectively, we get dx over dt, that is equal to kb into b minus x minus kf into a plus x. Now open the brackets. This will become dx over dt, that is equal to kb into b minus kb into x minus kf into a minus kf into x. This is equation number 3. Initially, the system was in equilibrium before perturbation. That is, initially the system was at equilibrium before perturbation, so the rate of forward reaction was equal to that of backward reaction. Therefore, Kb is equal to Kf, या Kf is equal to Kb. This is typographical mistake, plus written, but it is Kf is equal to, not plus but equal to Kb, or putting the value of this Kf into A is equal to Kb into B. Putting the value of Kfa in equation 3, we get, now we put the value of Kfa into equation 3, we will get dx over dt, dx over dt is equal to kb into b minus kb into x minus kb into b minus kf into x. Here kb into b or minus kb into b, they will be cancelled out. Then will equation will become minus kbx minus kfx. Minus x is written common. Then we will get dx over dt is equal to minus x into kb plus kf. Now separating the uh, variables and integrating this equation, we will get dx over dt, that is equal to minus kb plus kf into integration of dt, that is integration of dx over dt dx over x, that is equal to minus kb plus kf into integration of dt. Log x, integration of dx of x is equal to log x. Log x is equal to minus kb plus kf into t plus c. This is equation number 4. Once again, initially the system was in equilibrium before perturbation. So the rate of forward reaction was equal to that of backward reaction. Therefore, Kf is equal to Kb, not plus but Kf is equal to Kb, or we can write Kfa, that is equal to Kbf. Now putting the value of Kfa from this in the equation 3, we will get dx over dt, that is equal to kb into b minus kbx minus kbx minus kf into x. Now kb into b or minus kb into b, they will be cancelled out, and the equation will become dx over dt, that is equal to minus kbx minus kfx. Now we take the common minus x out, then minus dx over dt is equal to minus x into kb plus kf. Now separating the variables and integrating, we will get, that is x is taken on the left hand side and dt on the right hand side. The equation will become dx over x, that will be equal to minus kb plus kf into dt. Now integrating this equation, we will get integration of dx over x, that is equal to minus kb plus kf into integration of dt. Integration of dx over x, that is equal to log x, that is equal to log x is equal to minus kb plus kf into t, integration of dt is equal to t plus c, that is the integration constant, equation number 4. This is equation number 4. Now we can calculate the value of c, that is the integration constant, by putting the initial condition, that is when t is equal to 0, then x is equal to x naught. When t is equal to 0, then x is equal to x naught. Putting this condition in the above equation, we can calculate the value of C as C is equal to log x naught. C is equal to log of x naught. Now, sorry, putting this value of C in equation 4, we will get log x is equal to minus kb plus kf into t plus log x naught, that is the value of C. Log x is taken on the left hand side, then it will become log x minus log x naught, that is equal to minus kb plus kf into t, or we can write it as log x over x naught, that is log a minus log b, that is log of a over b. So similarly, log x minus log x is written as log x over x naught, that is equal to minus kb plus kf into t. Once again, when t is equal to 0, then x is equal to x naught. Putting this condition in the above equation, we can calculate the value of C as C will be equal to log of x naught. Now putting this value of C in the equation 4, we get log x will be equal to minus kb plus kf into t plus log of x naught. X naught is taken on the left hand side, then the equation will become log x minus log x naught, that is equal to minus kb plus kf into t, or this is written as log x over x naught, that will be equal to minus kb plus kf into t. Dear students, taking the anti-log on both sides, we have x over x naught. This will be equal to e raised to the power minus kb plus kf over t. Or x naught is taken on the right hand side, then x will be equal to x naught into e की power minus kb plus kf into t. This is equation number 5, where x represents the extent of perturbation at time t and x naught is the maximum possible perturbation. Dear students, the value of x decreases with time. Value of x decreases with time. The value of time at which x becomes 1 over e times of x naught is called relaxation period. That is the value of time at the time at which x becomes equal to 1 over e times of x naught is called the relaxation time. The expression for relaxation period in terms of rate constant can be obtained using the following condition. Condition is when x is equal to x naught over e, then t is equal to tau. T is equal to tau, that is the you can say the relaxation time. the period. By applying this condition to equation 5, we get x naught over E, that is equal to x naught into E raised to the power minus kb plus kf into tau. X naught from the left hand side is taken to the right hand side and it will divide. Then 1 over E will be equal to x naught and x naught will be cancelled out. This will be equal to E raised to the power minus kb plus kf into tau. Or we can write 1 over E as E minus 1, that is equal to E raised to the power minus kb plus kf into tau. As the bases of these two equal quantities are same, it implies that their exponents must be equal. That is, 1 is equal to kf plus kb into tau. From this we can calculate the value of tau. Tau is equal to 1 over kf plus kb. This is equation number 6. As the bases of these two equations, equal quantities, are same, it implies that the exponents must be equal. That is, 1 is equal to kf plus kb into tau. From this we can calculate the value of tau. Tau is equal to 1 over kf plus kb. This is equation number 6. Dear students, this equation shows that the relaxation period is a constant quantity and is equal to the reciprocal of the sum of rate constant for forward and that of backward reaction. Relaxation period for first order opposed by first order reaction is independent of initial concentration of A and B. That is, relaxation period is independent of initial concentrations of A and B. We can calculate sum of the rate constants for forward and backward reaction if the value of relaxation period is known. That is, we can calculate the sum of the rate constants for forward and backward reactions if the value of relaxation period is known. By knowing the value of equilibrium constant, individual rate constant can be calculated.